Structures and isomerism in coordination compound. Chapter 2. Coordination number of a metal ion in its complex is the number of donor atom attached to it. Coordination numbers and geometry of the complex are related to one another. For example, complex with coordination number 4 are either tetrahedral or square planar, and the complex with coordination number 6 are octahedral. The coordination number and geometry of the complex depend upon the following factors. Number 1. The size of metal ions or atom. Second, size of ligand and the steric interaction between the ligands. Third, electronic interactions and the number of d electron in metal ion or atom. Fourth, whether the ligand form pi bond with metal ions or not. In general, the metal atoms or ion of larger size, say 4D and 5D series transition metals and lanthanoids, favor the formation of complex of higher coordination number because steric repulsion decrease with increase in size of central metal cation. For similar reason, bulky ligands often form complex of low coordination number and the smaller size ligands form complex of higher coordination number. Complex of higher coordination numbers are formed for the central metal cation or atom of 4D and 5D transition element which lies on the left of the period and has a few number of d electron. The metal cation or atoms having a smaller number of d electron can accept more electron pair from the ligand. One ligand is MOCN84-. On the other hand, the metal cation which lies on the right of the period and are rich in d electron forms complex of low coordination number. A few examples are PtCl42- and PdCl42-, AgCl2-, etc. These atoms or ion can accept less number of electrons from the ligands. Complex of low coordination numbers are also formed when the ligands form multiple bond with metal cation, such as MnO4-, CrO2-, nickel CO4, etc. The formation of multiple bond between the metal cation and ligands oppose the additions of more number of ligands. The coordination number of the metal ions ranges from 1 as in ion pairs such as Na plus Cl minus in the gaseous state to 12 as in CONO3 6-2- ion. In general, the coordination number of metal in complex are found to be 2 to 9, out of which coordination number 2, 4 and 6 are most common. Coordination number 2. A few number of complex are known with coordination number 2. The complex with coordination number 2 are given by copper plus, Ag plus, Orium plus and mercuric 2 plus ion, that is D10 species. These complexes have linear geometry. Some examples are copper NH3 2 plus, copper Cl2 minus, copper NCN2 minus, AgNH3 2 plus, AgCN2 minus and AgCl2 minus, AuCl2 minus, AuCN2 minus, AgCN2, AgCH3 2, AuPr3 2 plus, etc. These complexes are typically unstable. Towards the further addition of ligand to form complex of higher coordination 3 or 4, such as copper Cn2- react with 2Cn-, copper CN43-, AgNH3 2 plus 2 ammonia, AgNH3 4 plus, AgCN2 2Cn-, AgCN4 2-. The cyano complex Ag and Au plus with coordination number 2 are less stable as they exist as discrete bis cyano complex. The solid K copper Cn2 contain a chain-like structure in which coordination number of Cu plus is 3. Figure chain structure of Cu Cn6 in solid form. The complex of coordination number 2 may also form by aesthetically hindered, that is bulky, ligands such as NSIPH32, NISEME32-, NSIMEPH22, etc. with metal ions such as Mn2 plus, Fe2 plus, CO2 plus and nickel 2 plus. One important example is FeNSiPH32. Coordination number 3. This coordination number is rare in complex and geometrics. Corresponding to coordination number 3 are trigonal, planar, and trigonal bipyramidal. Some famous examples are KCuCN2C, CSUCl3, infinite single chain, AJAI 3 minus, and pyramidal SNCl3, SNCl2 plus Cl minus, SNCl3 minus. Trigonal pyramidal structure of Cl3, coordination number 4. This is the second most important coordination number in coordination chemistry after coordination number 6, which is to be discussed later. The geometry corresponding to the coordination number 4 is tetrahedral or square planar. What is the geometry of coordination number 4? It's tetrahedral or square planar. What is the coordination? What is the geometry of coordination number 3? Trigonal planar and trigonal pyramidal. What is the geometry of coordination number 2? Linear geometry only. Yes. So the coordination number 4 geometry will be tetrahedral or square planar. Tetrahedral complex are favored when the ligands are larger, like Cl minus, Br minus, I minus, and the center metal cation or atom is smaller with D0 and D10 configurations and Dn configurations, where square planar octahedral is not favored by number of d electrons such as Fe2 plus D6, CO2 plus D7, Ni2 plus D8, CO2 plus D9, ion, which forms tetrahedral complex with Cl minus and Br minus ion. So tetrahedral complex is formed when the halogens act as a ligand. Halogens such as Cl minus, Br minus, I minus, and the complex forms square planar octahedral only when it is not favored by d electrons such as Fe2 plus, CO2 plus, D7, Ni2 D8, CO2 plus D9 ion. So this form tetrahedral complex only with ligands such as Cl minus, Br minus ion. The oxoanion of transition metal in high oxidation state are generally tetrahedral such as VO43 minus, CrO42 minus, MnO4 minus. Square planar complex are less favored sterically than tetrahedral. Therefore, these are prohibitively crowded by larger ligands. CO2 plus 3d7, Ni2 plus 3d8, CO2 plus 3d9 form square planar complex with pi acceptor ligands such as Cn minus. The metal ion belonging to 4d and 5d series transitions elements such as Rh plus ion plus Pd2 plus Pt2 plus EU3 plus form invariably square planar complex regardless of pi donor or pi acceptor character of ligand. Example of square planar complex are nickel CN42 minus, CuCN42 minus, UCN42 minus, CuNH342 plus, PdCl42 minus, PtCl42 minus, EuCl4 minus, RHMe3P3Cl IrCuMe3P2Cl. So square planar complex, is it less or more sterically favored? Square planar is less sterically favored than tetrahedral. Square planar accept which kind of ligand? Square planar accept pi acceptor ligand such as Cn minus. Which kind of metals? Okay, which kind of transition metals form square planar and accept pi donor or pi acceptor character of the ligands? The heavy transition elements such as Rh plus, iron plus, Pd2 plus, Pt2 plus, Eu3 plus. These transition metals are very big, very heavy, and it accepts both pi acceptor and the pi donor character of the ligand to form square planar complex. A. Tetrahedral. B. Square planar of complex of coordination number 4. A will favor tetrahedral if the ligands such as halogen Cl minus, Br minus, I minus. Square planar complex only form when the ligand is a pi acceptors, and if the transition metal is heavy, then it can accept either pi acceptor or pi donor character of ligands. But the transition metal should be very big and heavy. Coordination number 5. Complex of coordination number 5 are less common than that of coordination number 4 and 6. 4D blocks element. The complex corresponding to coordination number 5 are either square planar SP or trigonal bipyramidal DPP. Coordination number 5 complex hardly exist compared to coordination number 4 and 6. And which kind of geometry coordination number 5 shows? It shows trigonal bipyramidal TBP and square planar SP. However, both the geometry undergo some distortion from their ideal geometry. These two geometry can be interconverted by small change in bond angle because these two geometry often differ little in energy from one another. Mutiris and Gugelbergers has produced a series of coordination number 5 to show a sharp transition of an ideal trigonal bipyramidal to square pyramids. Okay, so does this show perfect square planar and or perfect trigonal bipyramidal geometry by coordination number 5? No, it shows some kind of distortions, and it is interconverted by having some changes in bond angle. Because these two geometry have difference in energy from one another. CDCl 3 minus trigonal pyramidal intermediate distorted PC6H55 COC6H7NO5 2 plus NiCN5 3 minus NBC NC5 H105 SBC65 H5 square pyramidal. Coordination number 5 complex. A chain from trigonal bipyramidal to the square planar. In some cases, it has been observed that polydental ligand and macrocyclic ligands favor the square planar geometries. For example, the iron atom in deoxyhemoglobin and myoglobins have square pyramidal coordinations. The phi coordinate Fe2 deoxyhemoglobin. So, which is there any example, any famous example which shows coordination number 5 and the ligands act as the macrocyclic ligands and the polydentate ligand? Yes, the hemoglobin, which is the protein of a blood, and the myoglobin. These two prominent proteins show coordination number 5, where iron atoms is attached to macrocyclic ligands, and macrocyclic ligands having 5 donor atoms. So deoxyhemoglobin and myoglobins shows coordination number 5 because ligand act as macrocyclic ligand. Macrocyclic ligands will always have more than 2 donor atoms. In fact, the deoxyhemoglobins is bonded to 5 donor atoms of microscopic ligands. So therefore, deoxyhemoglobin and myoglobins, they have coordination number 5 and they show square planar geometry. Square pyramid geometry. So deoxyhemoglobin and myoglobin show square pyramid geometry because coordination number is 5 and ligand act as macrocyclic ligand, and microscopic cyclic ligands have 5 donor atoms. So all these 5 donor atom is attached to the iron, central metal iron, and therefore deoxyhemoglobin and square and myoglobins show coordination number 5 and it shows square pyramid geometry. The NiCN5 3 minus ion exists as both square pyramid and trigonal bipyramidals in the same crystals. square pyramidal geometry, trigonal bipyramidal geometry. In general, trigonal bipyramidal with monodentate ligands are highly fluxional in solution. That is, a ligand that is equatorial at one moment become axials at the next moment. This change in positions of ligand may occur by Berry pseudo rotations. So these FeCO 1, 2, 3, 4, 5. So here the first, third and 5 carbon monoxide which is attached to iron atom is at the plane of paper, but in second carbon monoxide they are away from the observer, and the solid wedge carbon monoxide, the fourth one, is towards the observer. So what happens? This first and the fifth move away from the third carbon monoxide, and the second and fourth are at the same place. Then at the next moment the dashed wedge, the second carbon monoxide, move in between the first and the third carbon monoxide, and here the solid wedge fourth carbon monoxide is between the 1 and 5. So what is going on? So this shows this compound, okay, which is a monodentate ligand, this show trigonal bipyramidal, and this in the solution form is fluxional. That is a ligand that is equatorial at one moment become axial at the next moment. That's why the second and fourth carbon monoxide which were equatorial, okay, at the next moment this both the starched wedge and solid wedge carbon monoxide change from equatorial to the axials. So their position is changed because of Berry pseudo rotations. The FeCO5 complex, for example, is trigonal bipyramidal crystal. However, in solution, the axials and equatorial ligand exchange at rate such that this ligand cannot be distinguished by NMR, which has a time scale less than 10 raised to minus 3 seconds, and the 13 carbon NMR spectrum of FeCO5 shows only one resonance. This indicates that the exchange of axials and equatorial ligands takes place at a rate that is fast on NMR scale. It is also observed that the exchange of this ligand is slow on IR time scales. So FeCO5, this is a organometallic uh, organometallic complex. They show trigonal bipyramidal geometry in crystal form, but when this compound is changed into the solution, its ligands position change from equatorial to axials. The position of ligand is exchanged, and it is so fast that even NMR cannot detect these changes of position of ligand from equatorial to axials is done at the speed of less than 10 to minus 3 seconds, very quick, very fast. So the 13 carbon NMR also can't detect these changes. Only the IR NMR scale can detect the changes, because it is because the because this changes of position of a ligands is speed become slow in presence of IR time scales, but it is very fast on NMR scales. So we can study FeCO5 complex with the help of IR instrumentation, nor with the NMR, because the changes of ligands positions is very fast in NMR scale, but it is very slow in the IR scale. Coordination number 6. This is the most common and enormous important coordination number for transition metal complex. The possible geometry corresponding to coordination number 6 may be hexagonal, planar, trigonal, prismatic, octahedral, or tetragonally distorted octahedrals in regular octahedral complex. All ML bond distance are equal and the complexes have ligands, have plane as well as center of symmetries. In other words, we can say that regular octahedral complex are highly symmetric octahedral symmetries. Complex of Cr3 like CrH2O63 plus CrCN63 minus complex of CO3 like CH2O63 plus UNH363 plus COCN363 minus complex of Fe2 like FeCN64 minus complex of Ni2 like NiNH362 plus etc. The structure of regular octahedral complex is Ml6. So the transition number we show coordination number 6. They always show geometry such as hexagonal planar, trigonal prismatics, octahedral or tetragonal distorted octahedral. So which compound okay show octahedral, okay, in which condition? So a transition metal show octahedral complex when all the 6 ligands have equal bond distance, okay, and have center of symmetry. So means this octahedral complex have symmetrics and uh, have symmetrical geometry because of equal bond distance between the metal and ligands. Okay. So which kind of complex show coordination number 6 as well as symmetric octahedral? This is CrH2O63 plus CrCN63 minus. Okay. So at the coordination number at the oxidation state 3 cobalt. Okay. CH2O63 plus UNH363 plus UOCN63 minus. They show octahedral and their distance between the metal and ligands is same and equals. So Fe2 plus like FeCN64 minus also show coordination number 6 and octahedral. Nickel also in Ni nickel NH362 plus. These also show regular symmetrical octahedrals when metal and ligands have same bond distance. In structure of regular octahedral complex. Okay. Now, when different kind of ligand are present in octahedral complex, the symmetry of the true octahedron cannot be retained. Okay. There are some complex of coordination number 6 which have all the 6 ligand same but undergo some kind of distortion due to electronic effects. So what happened due to the electronic effects when the ligand is 6 and when the ligand is 6 makes coordination number 6 of a transition metals and they are in octahedrals, but due to the electronic effect what happened, all the 6 ligands get distorted. That means these they never show the symmetrical octahedral geometry because of electronic effect. The first is the tetragonal distortion, either elongation or compression along one of the four-fold rotation axis of the octahedral. This type of distortion has been discussed in Jahan-Teller distortion, Jahan-Teller effects. So, what the Jahan-Teller distortions or Jahan-Teller effects says when the octahedral which have coordination number 6 get distorted. When it distorted, it change into tetragonal distortions. Okay, where four-fold axis rotation are there. Okay, one remaining two is elongated and remaining four is compressed. Okay, around the rotational axis. So this kind of things happen due to the electronic effects when the octahedral is distorted, change into the tetrahedral where the 4 ligands are compressed, rotation 4 axis and remaining 2 are elongated axis. Trigonal distortions: A. Tetragonal elongation, B. Tetragonal compression. So when the octahedral is distorted, either show tetragonal elongation or tetragonal compressions. That means 2 ligand will be at the axis elongated, remaining 4 will be around the rotational axis. Another type of distortion is the elongation or compression called trigonal distortion along one of the 3-4 rotation axis of octahedron which passes through center of the faces, resulting in trigonal antiprisms. There is another type of distortion of octahedral which is called trigonal distortions when the ligand is elongated or complex. Okay, this show 4-3-4 rotations of octahedron and passes to the center of the faces and show the trigonal antiprisms. If the ligand of regular octahedral complex like CONH363 plus replaced by chelating ligands like diamine, NH2CH2CH2, NH2 to form CONE3 plus, the symmetry of regular octahedron is reduced from octahedral to D3, but it is not a real distortion. So COEN3 plus, okay, show octahedral which is reduced to D3, but it is not a real distortions. The complex having trigonal prismatic geometry 2.10 are rare, but have to be found crystal lattice of sulfur or heavy metal. For example, MOS2 and WS2 trigonal prismatic complex D0 complex such as cedar CSC62 plus WCSC36 has also been isolated. Trigonal prismatic structure of ReS2C2PH2. Trigonal prismatic structure of ReS2C2PH2. This kind of geometry is very rare in case of coordination number 6. Trigonal prismatic is very rare. Higher coordination number. Coordination number 5 is not common. However, it is encountered for few 3D and some 4D and 5D metals complex, where the larger center metal ion can accommodate more than 6 ligands. The geometry corresponding to the coordination number 7 are pentagonal bipyramidal, a capped octahedrons, and a capped trigonal prisms. These three geometries are shown 2.11 in a capped octahedrons and capped trigonal prisms. 1 ligands. The 7 ligand occupy one of the 8 faces. So, coordination number 5 is not common. And the center metal accept how many ligands? More than 6. So what is the geometry of coordination number 5 complex? Pentagonal bipyramidal. And other than pentagonal bipyramidal, it shows octahedron, a capped octahedron, a capped trigonal prisms. So yes, this coordination number 7 shows pentagonal bipyramidal, capped octahedron, capped trigonal prisms. These three complex, and it shows and this octahedron capped octahedron capped trigonal prisms have 7 ligands, show 8 faces. So this is pentagonal bipyramidal, the A. Then B, this is a perfect pentagonal bipyramidal of coordination number 7. Then here, when this coordination number 7 pentagonal bipyramidal is distorted into capped octahedron, which is NBF7, and then also change into cap trigonal prisms because of distortion of pentagonal by pyramidal. Some example of complex of coordination number 7 are ZRF7 3 minus COCN2 plus ReOCl 6 2 minus UO2H2O5 2 plus. Coordination number 8. Coordination number 8 can also not be regarded as common. The possible geometry for complex of coordination number 8 are square antiprismatics. So what is the complex of coordination number 8 is square antiprismatic, and it is very rare, and trigonal dodecahedral. So a coordination number 8 is very rare, and it shows two type of geometry, which is square antiprismatics, trigonal dodecahedrals. The two famous examples of this geometry are shown. So the coordination number 8 of molybdenum CnH shows square antiprismatics, and this one B1 show trigonal dodecahedrals of coordination number 8. Coordination number 9. Coordination number 9 is shown by some F block element because of their larger size. So which kind of element show coordination number 9? It is F block element in a tradition known because they are very big in size. Some important example are LnH2O9 2 plus, NdH2O9 3 plus. The example of coordination number 9 of the D block element is T6H9 2 minus ReH9 2 minus. The structure of ReH9 2 minus is this. So this is also coordination number 9 is very rare because the central metal ion should be very big enough to accept the electron from the 9 ligands. So most of the inner transition element, F block elements show the coordination number 9. Then coordination number 10. Coordination number 10 is encountered in complex of F block element M3 plus ion. For example, THOX4 H2O4 minus. It has coordination number of 10. The higher coordination number are rare with D block M3 plus ion because their smaller size may be responsible for ligand-ligand repulsion when they approach in the metal line. So coordination number 10 is shown by which element? Obviously the F block element because of the bigger size, and most of these F block elements are in the oxidation state of +3, and very rarely any D block element will show coordination number 10 because first of all the transition elements don't have the big size, and after all these 10 ligands will have a repulsion with each other, and the repulsion between the ligand is much more higher. So coordination number 10 of D block element is very hardly will exist. Coordination number 12. Coordination number 12 is also encountered in complex of F block M3 plus ions. An important example of CuNO36 through CeNO362 minus, in which each NO3 minus ligand behave bidentate ligands. If the size of a metal cation is small, then NO3 minus behave as a monodentate ligand. If, for instance, it acts as a bidentate ligand with a smaller cation, there will be the strain between the two donor oxygen of NO3 minus and the complex become unstable. If the size of metal cation becomes larger, then there will be the small or negligible strains between the two donor oxygen atoms of NO3 minus when it coordination number metal ion. Thus, NO3 minus behaves as a bidentate ligand. Now, this coordination number 12, obviously, a block element will show the coordination number 12. They have the capacity, their size is very bigger to accept the two pair of electron from 12 ligands, okay, but there is a one complex called CnO362 minus. Now it seems that there is 6 ligand is attached to Ce, but actually the coordination number is not 6, it is actually 12 because NO3 minus is act as a bidentate ligand. Both nitrogen and oxygen are two donor atoms make a bond with the CeF block element. Okay, because Ce is belong to a block element, inner transition element, and its cation size is very big. Okay, but if this same NO3 minus is making a bond with a small cation metal, then this NO3 minus will act as a monodentate ligand. But if this same NO3 minus act as a bidentate ligand, it is having a bond with a smaller cation, then there will be the strain between the two oxygen atom of NO3 minus. So what will happen, the small size cation, when it's forming a coordination bond with the two donor atom of the NO3 minus, that kind of complex will be unstable, because both the donor atom of two oxygen atom of NO3 minus will have a strains between them. So it is better the NO3 minus ion form a coordination number bond with the bigger size metal ions, so there will be no strains between the two oxygen atoms, and as well as because of the bigger size of the metals, this strains of the two oxygen atom will be negligible, and the complex which will be formed will be stable, and so NO3 minus ion can behave as a bidentate ligand. Isomerisms.